morning. Okay, 9:01. All right, how are y'all doing? Okay. All right, so we have a test on Thursday. I sent the review out over the weekend. It's a pretty long review. Let's talk about that at the end of class. Maybe save about 5-10 minutes. If you have any questions over any of the problems, I encourage you to come by my office and get help. All right. But at the end, I'll talk about like the length of the exam, because obviously it won't be as long as the review. So I'll kind of tell you what to expect. Okay, so we were doing the mean value theorem last time, and I've put the theorem over there on the side. That's not going to be on camera, but that way I can refer to it. The idea geometrically is that if we are given a function and we are defining that function on a closed interval, so we start at a point, we end at some other point. As long as that function is continuous, that means we can draw it without picking up our pencil. And as long as we can take the derivative on the inside, meaning there's no cusp or corners or anything like that, then we're guaranteed by the mean value theorem that somewhere in here there is a point. Well, let me go the other way around. If you connect these two endpoints with a straight line, that line has a slope, and that's called the slope of the secant line. And that is, by definition, f of b minus f of a over b minus a. So whatever the slope of that blue line is, somewhere in here, there's at least one point where if you go to that point and you find the slope of the tangent line at that point, we call this point C, the mean value theorem says there's at least one place in here where the slope of the tangent line will be parallel to the slope of the secant line. And that's what this is saying right here. The slope of the tangent line at that point C will be equal to the slope of the secant line connecting the two endpoints. All right, that's where we kind of ended class last time, right? And so I want to do an example. All right, let's just do an example, and then I think I'll answer that question about remember the cars, the racing cars? We'll do that, and then we'll move on to the next section. I guess I could have left that up there, sorry. All right, so let's do our first example. This is the way these problems will appear, all right? And this, of course, will not be on your test, right? But this would be on the final. So verify the mean value theorem I told you I would start abbreviating that MVT. Verify the mean value theorem for the function f of x equals, let's go with something like x cubed minus 3x squared plus 1 on the interval, let's go -1 to 2. All right. So what we're trying to do is verify that this mean value theorem is actually true. Like this is true. So first things first, is my function continuous? Because for the theorem you have to have a continuous function. So is this continuous? Yes? Why? It's a polynomial. Good. All polynomial functions are continuous. That comes from a theorem earlier in the class. Okay, it's continuous. All right. Next thing, is it differentiable? So can you take the derivative of this? Yes? And is that derivative a nice function? Well, let's take the derivative real quick. What's the derivative of this function? There's not a lot of work, right? 3x squared minus 6x. Right? That's our derivative. So it's differentiable. We could take the derivative of this. And when we look at this, right, there's no problems with it. Because again, it's a polynomial, isn't it? It's a quadratic. And so the derivative, the function is differentiable everywhere inside the interval. So I've got the first two conditions, right? Well, the only conditions we need, right? These are the only conditions you need for the mean value theorem to work. So I've got both conditions. That means the mean value theorem should apply. And now I just need to show, like verify that it's true. So what I'm going to do now is I'm going to erase this part. And I'm going to state the mean value theorem, and then I'm going to work with that. So I'm going to put, since both conditions were true, I'm going to put so. Let me move this up. It was x cubed minus 3x squared plus 1, and it was on the interval -1, 2, right? So here's what I can say. So there exists a c in the interval -1, 2 such that the following is true. F prime at C must be equal to f of b minus f of a over b minus a. Right? That's what the mean value theorem says should be true. Now for us in this problem, what's a and what's b? A is what? Yeah, it's the interval, right? So the a is what for us? A is -1 and b is 2. So what I'm going to do now is I'm going to write this equation again on the next line, but I'm going to replace my b with 2 and my a with -1. All right, that's f of 2 minus f of -1 over 2 minus -1. Right? All I'm doing there is replacing the b and the a. Any questions? All right, at this point, we got to figure out what all this is. All right, so let's talk about the left side of this equation. So when I work with this, I'm going to work the left and right-hand sides down like this. What is the derivative of the function if you plug c into it? So remember we did the derivative a second ago? The derivative was 3x squared plus, minus 6x, right? That was our derivative. What would you get if you plug c in for x? Well, you just get that with c's instead of x's, right? So that's the left side. 3c squared minus 6c that must be equal to whatever this is, all right? Now, what does f of 2 mean? Plug 2 into the original function, right? Let's do that just in our heads. If I plug 2 into here, I get 8, right? Minus, let's see, 2 squared would be 4. 3 times 4 is 12. So 8 minus 12, negative 4, and then plus 1, negative 3. So I trust all of you could just plug the number into that, right? Negative 3 is what we get. Then I have minus. Now, what happens if you plug in negative 1 into that? So let's see. If I plug negative 1 in here, what do I get here? Negative 1. What about negative 1 here? This is positive 1 and then times 3, right, which would be 3, and then subtracting it. So negative 1, take away 3, negative 4, plus 1, negative 3. You all right? So I'm subtracting negative 3 up here. Be careful. I'm subtracting negative 3. And that's all over what number? This is really 2 plus 1, right? So 3. Y'all have any questions to that? That's just plugging numbers into the function. Yeah, we're all right? Okay, I need to continue that. Okay, so I'm going to write the left side again. 3c squared minus 6c must equal, okay, what do we get up here? 0, okay. 0 over 3. And what's 0 divided by 3? Still 0, right? So you get 3c squared minus 6c equals 0. What type of equation is that you're looking at there? What type of equation is that? Is it linear? No. Y'all all right? Quadratic? Is that a quadratic equation? Yes? Right, the variable is squared. That's a quadratic equation. Can you solve quadratic equations? Should be able to, right? So when you get to a quadratic equation, you really have a couple of options. You can try and factor. If you can't factor, you have the quadratic formula. You can always fall back on the quadratic formula. But this, because there's a 0 on the right-hand side right now, this is actually going to be pretty straightforward. On the left side, I'm going to factor out a 3c. I'm going to factor a 3c out, greatest common factor out of both of these. They both have a 3, they both have a c, and if I do that, I'm left with c minus 2 equals 0. And then I set each of those factors equal to 0. So what are my two solutions? If I set that to 0, I get 0. If I set this to 0, I get 2. So my two answers are c equals 0, c equals 2, right? The mean value theorem says that there's at least one point, right, in there where the slope of the tangent line is equal to the slope of the secant line. And we're saying here that these are the two places it happens. See, the mean value theorem guarantees you at least one place, right? But this is saying we found two places. Now, we have to check, are these 2 points inside this interval? It's very important that you understand we're using the parentheses at the end of this, not the brackets. So are both of these numbers inside the interior of that? The 0 is, right? The 2's not. The 2 is at an endpoint. So we throw this one out because it's at the endpoint, not inside the interval. The theorem says you're going to have at least one point inside the interval where you're going to have the slope of the tangent line be equal to the slope of the secant line. All right, we're done. I know this is a weird problem because it's like, what are we trying to achieve? We're trying to show that the mean value theorem does in fact produce a C that's in that interval. Now let me show you, I want to show you visually what we just did. So if we go to Desmos and I graph the original function, x cubed minus 3x squared plus 1, and I restrict that between the interval -1 to 2. Move that over here. So if we take a look at this, here are two endpoints, right? And if we connect these two endpoints with a straight line, what's the slope of that line? 0. Do you remember on our equation we had 0 on the right-hand side? On the left we had 3c squared minus 6c, right? We were saying when is the derivative equal to the slope of the secant line? That slope was 0. Then we solved that and we got an answer of c equals 0. So now if you go to 0 on the x-axis, go to 0, which is right here, and go up to your graph and look at the slope of the tangent line there. What is it? It's 0, right there, parallel. They're equal. So we found exactly where it happens. Does that make sense to you? So what would happen if I give you the same exact problem, but I change the interval? Will we get a different answer? If instead of going from -1 to 2, if I go, let's say, -1 to 3, are we going to get a different answer? What do you think? Probably, right? Probably. Let's change it. Let's do it. Let's actually go through and just change the problem, change this to a 3, and let's see how that changes our work. Okay, so new example, same problem, just change the interval to 3. And now I'm going to go straight to the mean value theorem. We already know it's continuous. We already know the derivative exists. All that's still good, right? So we should have that the derivative at some value c that I don't know should be equal to f of b minus f of a over b minus a. And that means that 3c squared minus 6c, again, that's the derivative, plugging c into it. I erased it, but that's the derivative of this, plugging c into the derivative. And then now b is 3, isn't it, instead of 2? So when we plug 3 into this, we should get a different answer there, shouldn't we? I'll just keep working here. All right, let's plug 3 in to this. And this one, I won't do it mentally. I'll just do it over here, scratch work. If I plug 3 into the original function, that's 3 cubed minus 3 times 3 squared plus 1. 3 cubed is 27 minus, let's see, 3 squared is 9. 9 times 3 is 27, so 27 again plus 1. And then the 27s cancel out, you just get 1. So the top left corner of this is a 1. Minus, now we plugged -1 in already, hadn't we, before, previous example? What do we get? -3, right? -3, so it's minus 3. And then over on the bottom, 3 minus -1. So the top now becomes 4. Hey, check it out. And the bottom is also 4. We got lucky. This is 1, right? I don't like the way I'm doing that. Don't do that. Don't write that. Don't do it that way. Leave it like that. Okay, any questions? No? Next line, 3c squared minus 6c must equal, the top is 4, the bottom is 4, so it should equal 1, right? Not 0 this time. That 1 on the right-hand side, right? That 1 on the right-hand side makes a huge difference in terms of how we solve the equation. Because previously, on the previous example, this was 0, and then all I did was factor the left-hand side, right? Can't do that here. Because, well, that's a bigger question. If I did, don't do this, but if I did this, right, factor the left-hand side, if I wrote that down, can I say this next? These two things multiply to be 1. Do I set each one of them equal to 1? Is that a legal algebraic move? No, absolutely not. You can only do this if this is a 0, right? And it goes back to the idea that if I give you two things, let's call this A times this is B. If I tell you that two things multiply to be 1, does that mean that one of them has to be 1? If two numbers multiply to be 1, does that mean that one of them has to be 1? No. Can you give me an example of two numbers that multiply to be 1 where neither one of them is 1?
0.5 5 times 2.
Okay, so 1/2 times 2, right? 1/2 times 2, that would equal 1, but neither one of those is 1, right? This is called the zero factor property from college algebra. So the idea is that if two numbers multiply to be 0, then yes, one of them has to be 0. There's no way to get 0 multiplying two things together without one of them being 0. So what you do is you set them both equal to 0 and you figure out what makes them 0. But if it's equal to some other number other than 0, then you can't do it. All right? You with me? So we are sitting here at this point right up there. I see students do that all the time. Even my calculus students will do, my Cal 2 students, sorry, y'all are still calculus. My Cal 2s, I'll be like, what are y'all doing? No, you can't do that, right? So how are we going to do this then? It's still a quadratic equation, right? So how are you going to solve it? You can use quadratic formula, move the 1, right? So the standard approach for quadratic equations is to get everything over to one side, right? Everything to one side so that you can solve the equation either by factoring or by the quadratic formula. And unfortunately for us, this is not going to factor. All right, you can play with this all day long. You're not going to factor it. All right. So I'm going to now resort to the quadratic formula, which I know you've learned at some point in your life, right? So the quadratic formula says that if you have any quadratic equation, right, the solutions to this are negative b plus or minus the square root b squared minus 4ac all over 2a. I know you have all seen that, right? It's just maybe been a while. All right, so I'm going to use that formula for this quadratic. The c's are like the x's, right? The c's are like the x's. So all I have to do is identify a, b, and c here. So that's a, b is this number, right? And c is negative 1. And just crank out the formula. So watch what I write here. I don't write x, I write c because my variable is c. What's negative b? Because that's the first thing in the formula. What's negative b? What's the opposite of b? Positive 6, right? Because we have negative 6. The opposite of that would be positive 6. Plus or minus the square root of. All right, now I need to square the b. So negative 6 times negative 6 is positive 36, right? Then minus 4 times a was 3 and c was negative 1. And then all of this over 2 times a, which was 2 times 3. Get your calculators, because I want a decimal answer here. This will be 6 plus or minus square root. Okay, this turns into 36 plus 12. The way I look at this, because this is where most students screw this up, the way I look at this is that I count how many negative signs I see. If I see 2 negative signs, I know it's going to turn to a plus. If I see 3 negative signs, it's going to be a minus. So if you have an even number of minus signs, it's a plus. If you have an odd number of minus signs, it's a minus. So I see 2, it's even, so it's going to be a plus there, and then all over 6 again. Can I cancel these 6s? No, right? You have to be able to cancel 6 here, here, and over on this side. So don't cancel those. 36 plus 12, 48. So c is equal to 6 plus or minus the square root of 48 all over 6. Okay, what's square root of 48? Someone give me a decimal approximation of that. It's going to be like 6 point something. 6.92? Okay, 6.92 all over 6. And now I have to do 2 different scenarios. Do 6 plus this number, and then divide by 6, and then 6 minus this number, and divide by 6. So I need someone to help me out there. Anyone? Anyone? Yes?
For the first one, the plus, I got 2.153.
2.153, that sounds about right.
For the second one, I got negative 0.153.
0.153. Okay, that sounds right. We're about to check. All right, we'll see if these are right. So I got 2 answers, right? I should expect 2 answers with the quadratic formula. And so now, before I do anything else and say these are my answers, I need to check that whether or not these live in the interval we're talking about. Do they? Does 2.153 live in there? Yes. Does negative 0.153 live in there? Yes. That means there's two places where the tangent line should be parallel to the secant line when I graph this. So I want to go back to Desmos, and I want to change that 2 to a 3. That'll give me more of the graph. Let's move that graph here. Perfect, just like that. Okay, so now, if I take the two endpoints, and I connect them, right? The slope of that was what? Do you remember what the slope of that was? I heard it. 1, right? Because remember when we set up the equation, this right here? We were trying to figure out where the derivative was equal to the slope of the secant line. And this right-hand side, that right there, is the slope of the secant line. So this slope of this is 1. We're trying to figure out where else on the function do we have a tangent line that's going to be parallel to this. So I'll be kind of precise about this. F of x equals that. Okay, and now I want to plot. What did we get? We got, let's go with the negative one. Negative 0.153, right? Something like that. F of negative 0.153. Right there. Okay, that point right there. What we're saying is that if you were to get the tangent line right there, you would have parallel. I'll have the computer do it for us. Y minus F 0.153 equals there. Okay. Do they look parallel to you? Yes? And then we had another place, didn't we? So the other place was at 2.153. There we go. Those 2 points, right? I didn't have the computer put the point, but do y'all see right there? If I go here, take the tangent line, it's parallel to this. If I go here and take tangent line, it's parallel to that, all right? Okay, so the mean value theorem guarantees that you have one point within the interval where your tangent line is parallel to your secant line. Got it? Okay. For your homework for this, this is 4.2. For your homework, problems 9 and 10. 4.2, do problems 9 and 10. Keeping it simple, polynomial functions, nothing complicated, all right? I could give you more complicated functions, and then it would be more difficult to figure out, like to solve the equation. But I really just want you to walk away just knowing like what the theorem provides us, all right? So let me show you one quick application of this. And this is kind of leading us into the next section. So there's a problem in the book that I'm not going to assign, okay? And it says this. It says, show that this equation, 2x plus cosine x equals 0, has exactly one solution, period. That's it. So it's saying here, show that this equation has exactly one answer and one answer only. It's not asking you to find the answer. It's just asking you to show that there's only one answer. One value of x that you could plug in here and make this true. It doesn't seem like we should be able to answer this, right? Like this seems kind of challenging. Like how are we going to show that that only has one answer? So the first thing I'm going to do is I'm going to go back to something we learned earlier in this class, something called the intermediate value theorem. Intermediate value theorem, and you may not remember it, but maybe as I do this, I'll remind you. What I'm going to do is I'm going to pick some arbitrary points right now. I'm going to guess at some answers to this. So let me try 0. If x is 0, what do I get? Let's plug 0 into that. And let's look at it this way. Sorry, I should point this out. I'm going to look at the left side of this equation like a function. I'm going to call the left side f of x. So what would happen if I plug 0 into that function? What do I get? I get, so 2 times 0 plus cosine of 0. That would give me 0, and then cosine of 0 is 1. So I get 1, right? Yes? Okay, let me try, because I know where I'm going with this, let me just try another point. And I'm going to pick it because, like I just said, I know what's going to happen. I'm going to try -2. So if I do, well, you know what, let's go -1 to keep things nice. -1. If I plug that in, I get 2 times -1, right? Plus cosine of -1. That's going to be, what, -2 plus cosine of -1. Right, just multiplying those. And do you all agree with me that this has to be a negative number? Yes, no, maybe so. If yes, why? Why does that have to be negative? Any ideas? You got some?
Because you're doing the cosine of a negative number, and when you rotate backwards around your circle, you're going below the x-axis, so all your x values are negative.
Your y's would be negative. So that may not work.
No.
No, but it has to do with the cosine function. What is cosine bounded between? When you graph a cosine function, what is it between? The graph. What's the highest value of a cosine function? 1, and then the lowest? -1. So the biggest this could be would be a 1, right? +1. And what am I going to do to it? Subtract 2, right? So could this ever turn out to be a positive number? This right here would have to be bigger than what for it to be positive? I would have to be bigger than +2, right? Because if you add, like if I add 2 to this, I get 0, right? This plus 2 would be 0. But if it's any bigger than 2, then I would get positive, right? But it's impossible. It's impossible to make that bigger than 2. Does that make sense? So this can never be a positive number. It has to be negative. Now, why is that important? It's important because what I have